All right, let's get right into it. We're going to be talking about one of the most foundational, but also one of the most slippery concepts in all of system design, the transaction. It's this promise of order in a world that is, frankly, pure chaos.
So here's how we're going to tackle this. We're going to start with the beautiful, simple promise that transactions make. Then, we'll start peeling back the layers and get into the nitty-gritty, the complex reality of all the trade-offs, especially when things get distributed. So, first things first, why do we even need transactions? I mean, what's the core problem they're actually built to solve for us as engineers? Well, because let's be honest, the real world of data is a complete mess. You've got processes that just give up and crash mid-write, networks that decide to drop your precious packets, two people clicking save at the exact same time. It's a minefield. Without some kind of safety net, our data would just turn into garbage almost instantly. And this is where the magic of the transaction comes in. It acts like a funnel. It takes all of that chaos, all those potential disasters, and boils it all down to just two simple outcomes. Either everything works, and we call that a commit, or nothing works, leaving things as they were, and we call that an abort. Yeah, we give up a little bit of raw speed for this, but what we get in return is huge. Our data stays correct, and our application code gets way, way simpler to write. Now, this safety guarantee, it isn't just some fuzzy concept. It's actually built on four super specific pillars. You've probably heard of them, the ACID properties. I like to think of ACID as this impenetrable vault for our data. A is for atomicity, that's the all-or-nothing deal we just talked about. C is for consistency, which basically means your own application's rules are always enforced. I is for isolation. This one's huge. It's the illusion that your transaction is the only thing happening in the entire universe. And finally, D for durability. Once something's committed, it's there for good. Power outage? Doesn't matter. It's saved. But, and this is a huge but, there's a catch. This perfect vault comes with a price tag. Getting that perfect isolation, it's a really, really expensive in terms of performance. It creates bottlenecks, and it can grind your system to a halt. And this right here, this is the core conflict we're going to keep coming back to. The constant battle between perfect correctness and high performance. Okay, so with that trade-off in mind, let's get real. Let's start relaxing that perfect isolation just a little bit to see if we can squeeze out more performance. But as we do, you'll see we start walking into some interesting and dangerous territory. Think of this as our map for the journey. We're going to start down here at the bottom where the guarantees are a bit looser and climb our way up to the top, the gold standard, serialization. And along the way, we're going to meet all the weird little monsters, the race conditions, that pop up at each level. First up, the level most databases default to. Read committed. It's a good start. It stops you from seeing dirty reads, which is just a fancy way of saying you won't see someone else's half-baked, unfinished work. But it's vulnerable to something called a non-repeatable read. Imagine you read a value, do some work, and then read the exact same value again, and poof, it's different. Why? Because some other transaction snuck in and changed it right under your nose. Okay, so to fix that mess, we can level up to snapshot isolation. This is a massive step up. What happens here is the database basically takes a picture, a snapshot, of the entire database the second your transaction starts and says, here, this is your world, it won't change. The really cool part, which is usually done with MVCC, is that writers don't block readers, which is great for performance. But with great power comes, well, really subtle and nasty bugs. And that nasty bug has a name, write skew. I know it sounds super academic, but stick with me because the problem is incredibly common. It's when two different transactions look at the same data, both think, yep, everything looks good to go, and then they both make a change that when combined completely breaks the rule they were both trying to follow. The classic example makes this crystal clear. Right, the doctor's on-call problem. The rule is simple. We need at least one doctor on call at all times. So Dr. Alice looks at the schedule, sees Dr. Bob is on call too. Great, she thinks, I can take the night off. At the exact same time, Dr. Bob looks at the schedule, sees Dr. Alice is on call, and thinks the exact same thing. They both update the schedule, and suddenly, we have 0 doctors on call. Our business rule is completely broken. This is a classic phantom read. They were making decisions based on the count of doctors, a phantom piece of information that was invalidated by the other's action. And here's the key takeaway. The database has no idea about your doctors on call rule. All it sees are 2 perfectly valid updates. It's not smart enough to understand your application's logic.
To automatically prevent this kind of subtle bug, you have to go all the way up to the highest and, yes, most expensive isolation level, true serializability. All right, we've seen the dragons that live in the lower levels of isolation. So the big question is, how do we get back to that promised land, to serializability, without grinding our whole system to a halt? Well, there are basically 3 schools of thought on this. The first is just do things one at a time, literally, single-threaded. Super simple, but obviously it's not going to win any speed contests. Then there's the old school pessimistic approach, 2-phase locking. Basically, you grab a lock on anything you even look at and don't let go. It's safe, but it's awful for concurrency. And then there's the optimistic way. This is where serializable snapshot isolation, or SSI, comes in. It's optimistic, meaning it lets everyone run ahead, hoping for the best. Then, right at the last second before committing, it checks, hey, did we just create a right skew situation? If the answer is yes, it just aborts one of the transactions and makes it try again. So you get the safety of running one at a time, but the performance of running in parallel. The catch? Your application code has to be ready to catch those aborts and retry. Okay, so we finally figured out how to make things work on a single machine. We feel pretty good about ourselves. And then someone says, let's distribute the database across multiple machines. And suddenly, we're not climbing a mountain anymore. We're staring into a giant chasm.
See, on one machine, everything is neat. But when you distribute it, that clean vault shatters into what I call the distributed ocean. You lose everything you took for granted. There's no single source of truth for time, no global transaction counter. Trying to get all these different machines to agree to commit at the same time over a flaky network, it's a nightmare. It forces you into a terrible choice. Either your system becomes painfully slow, or you have to give up on some of those safety guarantees.
So, if it's that bad, how does anyone build a large-scale system? Do the big tech companies just cross their fingers and hope for the best?
No, the answer is they get pragmatic. They realize that old-school protocols like 2-phase commit are just too brittle. If that one central coordinator machine dies, your entire system can get stuck forever. That's a non-starter. So instead, modern systems push the responsibility up to the application. Instead of relying on the database to work magic, developers use clever tricks like idempotency keys. You send a payment with a unique ID. If the network hiccups and you send it again, the system sees the same ID and just says, nope, already did that one. You get the same result as a perfect transaction, but without the fragile blocking protocol. So if you remember nothing else, remember these 3 things. 1, isolation is not an on-off switch. It's a spectrum, and every step on it involves a painful trade-off. 2, you have to know your database inside and out. What one database calls repeatable read might be totally different from another's. And 3, the second you go from one machine to many, the second you cross that distributed divide, all bets are off. It's a whole new ballgame. And I guess the final thought is this. As architects, we're not looking for a silver bullet. There isn't one. The real job is to understand the history here, to know that every database feature exists because someone, somewhere, had a really, really bad day. Our job is to understand this landscape of trade-offs and to very deliberately, very consciously pick the right set of compromises for the problem we have right in front of us.